Hi students, welcome to my lectures on chemical reaction engineering. In the today's lecture, we are going to go through summary of what we have learned for the batch, CSTR and plug flow reactors. So to keep it more simple, and what I have drawn the specific reactor and the design equation and graphical explanation. This is the flow we are going through right now. This is the batch reactor. What we have discussed, that Vb is the volume of the batch reactor. At time t equal to 0, initial moles is Na0 in the batch reactor, initial concentration is Ca0. At time t equal to t, initial moles is, that means after certain time of reaction, the final moles is Na and final concentration is Ca. Given this conditions, what is the time required for given conversion or reduction in concentration? Na, integral Na to Na0 dNA by minus Ra into Vb. This is the design equation to find time to reduce the moles of reactant from Na0 to Na. Similarly, in terms of concentration, time required for the reaction to reduce the concentration of feed from Ca0 to Ca, what is the time? That means if you know the rate of reaction, that is if it's 0 order, first order, second order, you can put that expression, integrate or get the time. The second way is through graphical format. This or this, any one you can choose. If you choose moles as your graphical format, then the graph should be based on 1 by Ra into Vb on y-axis, moles on x-axis. If you have the data of y and x, plot that particular graph and find out the time. If you know the graph, then you can area under the graph will give you time. What are the limits you need to put? That means if you know this graph, what is the time required for a given batch reactor to reduce the moles from initial moles Na0 to final moles Na. That means between these limits, if you get the area under the curve which is A1, nothing but the time for the given reaction. Similarly, if you take this equation, you have to plot 1 by minus Ra on y-axis, this dCA means concentration on x-axis. Now, if you know the data points, plot the graph and estimate the time between what limits? From initial concentration from Ca0 to final concentration, what is the time necessary for this reduction in concentration in a batch reactor of volume Vb. So, this is the graphical procedure. The same statement I have given. The area under these particular graphs will provide the time necessary for a given concentration to reduce from initial concentration Ca0 to Ca in a batch reactor of volume Vb. This is how we have to proceed with the batch reactor. Let us come to the CSTR. You know, initial molar flow rate, initial concentration, initial volumetric flow rate. These are the final molar flow rate, final concentration, final volumetric flow rate. Okay. This is also Ca. Inside the tank also the concentration is Ca. Exit to the tank is also concentration Ca. Now, volume of the continuous stirred tank reactor for a given change in moles. That means, you know, initial the molar flow rate of A is Fa0 will be higher. After the reaction, the A is coming out at a lower flow rates because most of the A got reacted to form product. So, volume of the CSTR required to reduce the molar flow rate of A from Fa0 to Fa. What is the volume? Okay, nothing but Fa0 minus Fa by minus Ra. If you know the rate, speed of the reaction, then you can estimate what is the exit molar flow rate Fa given the initial molar flow rate Fa0. Similarly, this is in terms of flow rates and this is in terms of conversion. Volume of the CSTR required for a given conversion, that is for 80% reaction, for 90% reaction, for 50% reaction, what is the volume of the CSTR that is needed? Fa0 by minus Ra into x. If you know these, Fa0, that is a given molar flow rate, initial molar flow rate, and if you know the speed of the reaction in the reactor, and for the given conversion, 50% conversion, this much volume of the reactor is needed. The graphical way. Here, if you know the rate using analytical equations, if you know the rate, 0 order, first order, second order, or reversible reactions, or imagine that different kinds of reactions, what is, if you substitute and if you know find out this term and you get the volume. Okay, graphical way. If you see this equation, you have to plot Fa0 by minus Ra in y axis, x is on x axis. Now if you know the data, Fa0 by minus Ra versus x, if you know the data, plot this blue curve. Okay, now once you get the curve, find out the volume. What volume? For a given conversion, example, this is your targeted conversion, that means example 90% conversion. Draw a straight line and draw a horizontal line, and the area inside the box, that means area under the curve and area above the curve, A1 plus A2. If you find out the both areas, that means area of the rectangle is nothing but volume of the CSTR required for given conversion. Okay. That is what it is written in the statement. Area of the rectangle, that means this area, will provide the volume of the CSTR needed for a given conversion x. So let us go for the plug flow reactor. You know, initial flow rates, initial concentrations, final flow rates and final concentrations. Volume of the plug flow reactor needed for reduce the molar flow rate of A from Fa0 to Fa. Molar flow rate of A reducing means A is getting reacted. Then given reduction in molar flow rate, what is the volume of the PFR needed? That means you have to integral Fa to Fa0 dFA by minus Ra. In terms of conversion, 0 to x, that means here it is 0% conversion, it is some 80% conversion or 70% conversion. Given the conversions, what is the volume of the PFR needed? You can use both the equations. Okay. Then here the trick is, here you don't have integration. See, here it is a plain formula. Here it is an integration. Here x, this is dx, 0 to x Fa0 into by minus R into dx. It is simple, Fa0 by minus R into x. That means if you have the data Fa0 by minus Ra into and x, plot the curve, and for a given conversion, example, if your target conversion is this, draw a straight line. Okay, then between these two limits, 0% conversion and x% conversion. Similarly, this is 0% conversion, this is targeted conversion. Then because it is integration, here it is no integration, here is the integration. That means only area under the curve you have to take into consideration. Here because there is no integration, entire area above the curve and below the curve, that means entire box you have to consider. Okay. Here only A1, Fa0 by minus Ra is nothing, and area under the curve, that is only A1, is nothing but the volume of the plug flow reactor is needed for certain conversion. Observe these both curves. Always the rectangle area will be higher than the area under the curve. That is why for this particular scenario, always and always volume of the PFR will be less than volume of the CSTR, because A1 is less than A1 plus A2. This is A1, this is A2, here only A1. That is why for this kind of scenarios, you always expect that volume needed for a given conversion for a plug flow reactor is always less than the volume needed for the CSTR for the same conversion. And can I make a general statement? No. For this nature of the curve, this is valid. If the nature of the curve is in the other way, then things will be different. We are going to discuss in the next lecture. Okay. I hope you have learned the summary of the reactors. Let us meet with the new lecture. Thank you.